Hello guys. Alright, so I hope you guys got the homework with the solutions. So I hope the solutions were clear enough. But if you would like me to answer anything or explain anything in more detail right now, then I can do that for you. If you have any questions about the homework, you can put those in the chat. So 2 more minutes. Hello. So if you just came in, and you would like me to explain any of the problems on the homework, you can type those in the chat. But I think the solutions I think I made them pretty clear. But if you do need me to explain any of them, feel free to do so. Okay, so get the PowerPoint up. All right. So once again, it seems that we have 12 people today. So it's getting less and less every day. So I understand this is, like I explained this last time, but physics is a very, very difficult thing to do. It's an extremely difficult course. And so the fact that you guys keep going, never giving up, that's something, that's a good trait. With anything that's difficult, as long as you keep going, you're bound to make some kind of improvement in the field. Okay, so let's get started. This week for physics, we're doing an introduction to momentum. And the next week, we're going to get more in depth into applications of momentum in real life. Okay, so let's get going here. The topics we're going to go over today. First, we're going to talk about what momentum actually is. And then we're going to talk about the center of mass. And then the conservation of momentum. The conservation of momentum is a lot like the conservation of energy, except with this new thing we call momentum. All right. So first of all, momentum. What is momentum? In physics, momentum is defined as an object's mass times its velocity. So we have a ball of mass m and it's moving this way at some kind of velocity, then its momentum is defined as the mass times the velocity. I think we sometimes label this as p. Okay, p for momentum. All right, so the momentum is defined as mass times velocity. So both mass and velocity contribute to momentum, which means that a heavier, let's say a heavier truck versus a lighter car, the truck will have more momentum if they're moving at the same speed. Alternatively, if the car were to move faster, a lot faster than the truck, then the car would also have more momentum. So both mass and velocity um, are contributed into momentum. All right. So when I was learning momentum, I had some trouble visualizing what it actually was. Like, how do I visualize how momentum is a quantity? Like force is a quantity because I can visualize a force as I push a box, right? I can visualize that force. But how do I visualize momentum? Well, here's an example for you, make it a little easier to understand. Let's say we have a sumo wrestler here, all right? And your goal is to try to knock this guy down, all right? So how do you knock this guy down? Well, if you were to have a small child who has a very small mass, and this child were to charge at the sumo wrestler at a small speed, then obviously the sumo wrestler wouldn't be knocked down. But if the child were to go at a very high speed, extremely high speed, then such high speed allows the child to knock the sumo wrestler down, right? So this is momentum. If the child has enough momentum, then the child will be able to knock down the sumo wrestler, all right? Another way to see this is that if you were to replace the child with a larger person, maybe another sumo wrestler, you don't need as much velocity because the mass is now a lot greater. And this sumo wrestler doesn't need to have as much speed to knock the other sumo wrestler down. So that's how I would visualize momentum. Momentum is basically the amount of, it's almost like energy, but like it's kind of like the moving, like the ability to cause change in another object when you're colliding into it. For example, when the first sumo wrestler has momentum, this momentum is transferred to the other person, which causes the other person to get knocked down. So that's basically how I would visualize momentum. So it's another thing we should know about momentum. Like with energy, we've related energy to force. The change in kinetic energy equaled force times distance, right? Work. So how do we relate momentum to force? Well, we know that if we apply a force to an object, its momentum will change, right? For example, if this mass m was going slower, and then we would apply a force to accelerate it, then its velocity would change, and it would be a lot faster, greater velocity, which means a greater momentum. So there's some kind of relationship between force and momentum, and change in momentum specifically. So what is that relationship? Well, the change in momentum is defined as force times the amount of time it's been applied. The proof for this is actually quite simple. mv equals f equals ma, right? So ma times t. As you can know, a times t is just velocity. So mv equals mv. So that's the proof for the relationship between force and momentum. So the change in an object's momentum equals the force being applied to it multiplied by the time in which this force is being applied. So there's a really key difference between the change in kinetic energy and the change in momentum. Kinetic energy was defined as force times distance. Momentum is defined as force times time, okay? So that's a key difference here. And the term F times T, there's a special word physicists use to describe this term. This term is called impulse. So that's what we call this. When someone asks for impulse, impulse is defined as force times the time, okay? So this is what we define as impulse. And we're going to go over some problems about impulse later on. So another way to visualize impulse is that since these two are equal, then impulse is also change in momentum. So impulse is defined as the change in momentum of an object, and impulse is also defined as force times time. All right, so that's called impulse. Okay. So another way we can write this equation is momentum final minus momentum initial equals force times time. Because that's the definition of change in momentum. So these are two ways you can define the relationship between momentum and force. Final momentum minus initial momentum equals force times time. All right. So you may ask, hey, what are the units for momentum, right? We should know the units. Well, for energy, we had joules. That was kind of like a special unit we had. But for momentum, we don't have a special unit. Momentum is just kilograms times meters per second, right? Because mass is in kilograms, velocity is in meters per second. So momentum is just in kilogram meters per second. All right. And when we do problems with momentum, there's one key thing you guys have to remember. Since we're dealing with velocity and force here, we have to define a positive and negative direction. Because velocity can be either positive or negative, right? If it goes in one direction, it might be positive. If it goes in the opposite direction, it will be negative. So in momentum, when you do momentum, you have to define a positive and negative direction. All right? So that's a really important thing to remember. Okay, are there any questions about how momentum works? All right. So to recap, the momentum of an object is its mass times its velocity. And the relationship between momentum and force is change in momentum equals force times time. All right, and this is called impulse. The term force times time, impulse. Okay, so that's what it's called. Okay, so let's do some problems with these. So 3 problems here. I'll give you guys 5 minutes to do these. So once you get your answer, please chat that to me. And if you want to explain your solution, please let me know as well. Right, so Fiona will be answering the solution for the first problem. So if you got the answers for the second and third problems, I will let you do those if you want to. All right, 2 more minutes. All right, so that'll be time. So now Fiona will explain the first problem. So go ahead.
Okay, so since momentum is just mass times velocity, to solve for momentum, you just go 3 times 8, which is equal to 24 kg times m over s. For kinetic energy, that's it would be a bit more complicated. It would be 1/2 m, which is 3, and v squared, which is 8 squared. And when you solve that, you get 96 joules.
Yep, that's correct. So now I'm going to explain the second problem because no one wanted to do that one. So a truck weighs 5 times as much as a car. If the vehicles have the same momentum, what's the ratio of the speed of the truck to the speed of the car? Well, the momentum of the truck is defined as mass of truck times velocity of truck. And this is equal to the momentum of the car. Mass of car, velocity of car. All right? So a truck weighs 5 times as much as a car, which means that the mass of the truck is 5 times the mass of the car. So we can replace mass of truck with 5 times mass of car. So as we can see here, mass of cars will cancel. So 5 truck velocity equals the car velocity. So for ratio of speed of truck to speed of car, that's just 1 to 5. All right, if you were to rearrange this equation. Okay, so now for the last problem, I'm going to allow Tyler to explain that one. So go ahead.
So the last one is asking for impulse and the average force applied on a 3 kilogram ball at rest after 5 seconds that moves at 7 meters per second. So you first have to find the force applied, and using Newton's second law, that's F equals ma, and you already have m, so you have to find a is equal to the final speed over the amount of time, which is 7 over 5 meters per second squared. So using that, you can find that the force is equal to 4.2 newtons, and that's the average force. Then you have the impulse, which is force times change in time. We already know the force, so that is just equal to 4.2 times 5, which is 21 newtons.
Yep, that's correct. So what Tyler did here was he first found the force by F equals ma. He found the acceleration to be 7 over 5. So what he used here was actually the kinematic equation, A equals change in V over time. So the ball went from rest to 7 meters a second, so the acceleration would be 7 over 5, right? So that's how he did his problem. How another way you could do it with momentum is by saying the change in momentum equals impulse, which is I, we can say that as I, and impulse equals force times time. So using momentum, we can solve this as well. So change in momentum, initially it's 0. In the end, it's going to be moving at 7 meters a second. So 3 times 7 equals impulse, which will also be 21 kilogram meters per second. And so with impulse, 21 equals force times time, divide by 5, force also equals 4.2 seconds, 4.2 newtons, sorry. All right. So there are two ways to do this problem. One way was with kinematics, and then the second way was to use momentum. So you can do it either way. All right. We have these two problems here going further into what impulse is. So take around about 4 minutes to do these two problems. So how about this? Let's, for the sake of time, skip the second problem here. So skip this one. So if you're confused about what ms is, ms refers to milliseconds, which is 1/1000th of a second. All right, one more minute. All right, so seems like this problem is a little tricky for people. And so this kind of problem is actually very, very common with momentum. It's actually very tricky. So let's read this problem. You bounce a 2-kilogram basketball on the ground. Just before it hits the ground, the ball moves at 6 meters a second, bounces from the ground at 3 meters a second. What was the impulse delivered by the ground? So the answer most people would give is, hey, 3 and 6, right? So the initial momentum is 12. The final momentum is, what is it? It's 6. So that means the change in momentum, 12 minus 6. Oh, that's the impulse. But no, this is not right. So why isn't it? Well, if we draw a diagram out, it actually makes it look a little clearer. So let's first draw a diagram. Initially, the ball is moving downward at 6 meters a second. After it bounces, it's moving upward at 3 meters a second. So the velocity of this ball is going in different directions now. So one of these is going to be positive, one of these is going to be negative. So let's just set the positive as up and negative as down. So that, and the impulse is obviously going to be kind of like the normal force. It's going to be exerted upward by the ground. So the force will be positive, the initial speed will be negative, and the final speed will be positive. So let's set up the change in momentum equation again. Force times time, which is impulse. So this will be the final momentum minus the initial momentum. So what's that going to be? 3, which is positive, times 2, minus negative 6, because here the velocity is negative, times 2. So that's going to be the impulse. So in the end, it's going to be 3 times 2 plus 6 times 2, or 18 kilogram meters per second. All right, so that is the impulse. So drawing on a diagram makes it clear that since the velocity is in different directions, we have to make one of them positive and the other one negative. So then average force, we just use force times time equals impulse. So force times 0.003 equals 18. Solving for force, we get 6,000 newtons. Okay, so you can see this kind of problem a lot. It's actually a very tricky problem. Okay, any questions? All right. So now we have a final problem about generally momentum and impulse before we go on to the other parts of class. So given what you know about momentum, I'll give you guys 3 minutes to do this one. All right, so I'm going to explain this problem now. So this one is actually a little different because you have to break the velocity down into separate x and y components. So if we go way back to 2D kinematics, we know that the velocity in the x direction is independent from anything that goes on in the y direction. All right. So what that means is that when the ball is moving at an angle, it has both x and y momentum. It's going downward and into the right at the same time. And the thing is, momentum will only change if force is applied. So the ground will deliver impulse in the y direction upward, but it's not going to do anything to the momentum in the x direction. So the momentum in the x direction before and after the bounce is always going to stay the same. All right. And it's just the y momentum that's changing. So how do we find that? Well, it's moving at 4 meters per second at an angle of 50 degrees. So to find x momentum is just 4 cosine 50, y momentum 4 sine of 50. Okay. Now what? Well, after the bounce, we know that the x component of momentum is still going to be the same, 4 cosine 50. But the y component of momentum has changed because some kind of impulse was applied to it. All right. So what's it going to be? Well, the initial momentum downward is 4 times the sine. Well, that's the velocity actually. 4 times the sine of 50. So what we can do is we can do impulse 9.7 equals. Well, first we need to define positive and negative directions. Once again, let's just say upward is positive, downward is negative. So the force is going to be upward. So the impulse is upward too. So the initial speed, well, now it's going to be mv final minus mv initial 9.7 equals, well, we're going to try to solve for mv final minus 2 times negative 4 sine theta. All right, because it's going downward. So now we solve for v final. So 9.7 minus 2 times 4 times the sine of 50. Let me do that real quick. And then we divide by 2. So we're going to get 1.78 as the final momentum, final velocity. So after the bounce, it's going to be moving up at 1.78 meters a second. And simultaneously, it's going to move right at 4 cosine 50. Let me calculate that real quick. 2.57. All right, so now we can calculate the overall velocity of the object with the Pythagorean theorem. And then we can use the range formula to find how far this will go. So using the Pythagorean theorem, 1.78 squared added to 2.57 squared, take the square root. It's going to be moving at 3.13 meters a second. And what's the angle? Well, the angle is 10 of negative 1, 1.78 over 2.57. Right, this is just the kinematics. So 1.78 over 2.57. The angle is going to be 34.7 degrees. So now we just use the range formula to calculate how far it will go. Range formula, if you remember, it's v0 squared sine of 2 theta over g. So theta is going to be 34.7. So sine of 2 theta multiplied by v0, 3.13 over 9.8. So distance will be 0.94 meters. All right. So basically you had to break the velocity down into x and y components, and then you calculate the momentum in that way. And I think the trick in this problem was to realize that the impulse delivered by the ground can only go upwards. Because when you're standing on the ground can't push you left or right. You can only push stuff upwards. Okay? So any questions about this problem? All right. So now we need to talk about something called center of mass. We all know what center of mass is, right? If we have some kind of object, then all its mass, we can consider itself as a point mass at some kind of position, right? That's called the center of mass of the object. So how do we calculate center of mass? Because later when we talk about more advanced types of momentum, center of mass will be critical to those calculations. So what is the formula for center of mass? Well, if we have a bunch of objects in a plane, all right, let's say that this one has position x1, this one has position x2, this one has position x3, and their masses are m1, m2, and m3. Then the formula for the position of the center of mass, well, intuitively, it's going to be somewhere over here, right? This is going to be xcm. But the formula for center of mass is going to be xcm is equal to m1x1 plus m2x2 plus m3x3 over m1 plus m2 plus m3. So that is the formula for center of mass. We take the mass of every object multiplied by where it is, and we add all those together, and we divide through by the sum of their masses. And this formula works for however which many objects we may have, right? We can add an x4, an m4x4, and dot 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 mn xn. Right? We can have however which many objects we have, but we just need to divide it through by its mass in the end. So this is the formula for the position of the center of mass. So I would advise you guys to write this down in a notebook or somewhere. So this is the formula for where the center of mass is going to be. Okay. The center of mass is not limited to one dimension. We can have objects in a 2D plane. So how we find the center of mass in that situation is where we would just calculate the x component of center of mass first, and then calculate the y component, because these things are going to be separate. All right. So if we have a situation where the objects are in a 2D plane, then we would calculate the position of center of mass with x, the x coordinate first, then we would do the y coordinate. And these two things are independent. All right. And there's another common instance of center mass where these objects aren't stationary. They're moving in some kind of direction, right? They have some kind of velocity. And the same formula applies if we want to calculate the velocity of the center of mass. We just have to replace every single x in this equation with a v. All right. So we can use the same formula for the center of mass, the velocity of the center of mass, just by changing all the x's into v's. All right. Because if we have a bunch of masses moving, the center of mass must be moving in some direction, right? And that's how we would calculate the velocity of the center of mass. Okay, any questions about this? So that's the formula for center of mass. All right, let's do these three problems here with the center of mass. These shouldn't take that long. They're just direct applications of the formula. So how about 3 minutes? So Fiona will be explaining the first problem. All right, one more minute. All right, so now Fiona will be explaining the first problem. So go ahead with that one.
Okay, so since the center of mass is equal to the object's mass times their location all over the sum of their mass, 6 times 0 is just 0, so we can ignore that. And 8 times 13 is 104. And over the sum of their mass, that's 6 plus 8 is equal to 14. And when you divide 104 by 14, you get about 7.43. X is equal to 7.43.
And so nice job. And you know that that answer makes sense because if you were to draw these out at 13 here, 8 is at 13. So 7.43 is kind of like here. So it's closer to the 8 intuitively because the more massive object kind of attracts the center of mass towards itself. Okay? Now for the second problem, on the coordinate plane, a 7 kilogram ball is at 2, 3, 6 kilogram ball at 9, negative 9, 0. Where's the center of mass? Well, once again, we can calculate this separately. The center of mass x position is separate from the center of mass y position. So we can just calculate the x positions. 7 is at 2, 6 is at negative 9, 7 times 2 plus 6 times negative 9, all over 7 plus 6. So that's going to give the x position. And then for y, we just take 3 and 0. 7 times 3 plus 6 times 0 over 7 plus 6. And if you were to solve each of these, you would get negative 3.1, 1.6. That would be the coordinate of the center of mass. Okay? Now for the last problem, we have 3 masses moving, and the 4 kilogram mass is moving to the left at 3 meters a second. The 6 kilogram mass moves to the right at 1 meter a second, and a 3 kilogram mass moves to the right at 5. What's the velocity of the center of mass? Well, we can use the formula for the velocity of center of mass, which is m1v1 plus m2v2 plus m3v3 all over m1 plus m2 plus m3. Basically the same formula, except we replaced all the x's with v's. Okay? But the problem with velocity is that if an object goes to the left, and we set that as positive, then the object going to the right must be negative. Okay? So velocity has direction, so we must pay attention to the signs. So let's first define where our positive and negative is going to be. Let's just say, let's just have the positive direction as right, the negative direction as left. So what this is going to be is 4 times negative 3, because it's going left, plus 6 times, what's that number there? 6 times Sorry guys, I didn't know I was muted. So if you're to solve that over 4 plus 6 plus 3, then let's see. Negative 12 plus 6 plus 15 over 13. 0.69 meters a second. Okay? And which direction is it going in? Since we define the positive direction as right, and this is positive, then it means it's going at 0.7 meters a second to the right. All right. So skip this guy for now, and let's go on to the conservation of momentum. So just like with energy, we had conservation of energy, and for momentum, we have something called the conservation of momentum. And the definition of conservation for momentum is momentum stays constant in a system. Let me use my pen. If no net force, no net external force So this is the statement that defines conservation of momentum. The momentum of a system stays constant if there's no net external force applied to it. So this comes just directly from the change in momentum equals force times time, right? Because if we have a force, then we have change in momentum. If the force doesn't change, then the momentum doesn't change either, all right? So if there's no external force being applied to a system, then the momentum of the system and as a whole stays constant. So let me give you guys an example here. We have an object moving to the left, an object moving to the right. If there's no force being applied to any of these two objects, then their momentum will stay constant forever and ever and ever. Okay? And you may be asking, what do you mean by external force? Well, let's just say we have two guys in space. They're just floating in space. If the first guy punches the other guy, then that projects the second guy backwards, right? He's going to gain momentum. But the net momentum of the whole system of the two guys doesn't change. So as a result, the left guy moves left to balance out the momentum of the right guy. And this comes directly from Newton's third law of motion, right? Because if the first guy punches the second guy, a force is applied to the second guy. But an equal and opposite reaction force is applied to the first guy. As you can see here, the two forces balance out in the entire system. So even if there is force applied to a system, as in this punch, as long as it's internal and happening between the objects, then it's not going to change the momentum. Only if an external force, let's say there was a planet here that attracted them with gravity, in that instant, then the momentum would change. But otherwise, momentum is conserved. And what this also means is that if we have a system of objects moving, let's just say we have mass 1 moving this way, mass 2 moving this way, their center of mass, the momentum of the center of mass of these two objects, the velocity specifically of the center of mass stays constant. Right? Since the momentum of these objects stays constant as a whole, then the velocity of the whole system stays constant. And that's where the center of mass comes in with momentum. So the velocity of the center of mass of a system stays constant when momentum is conserved. Okay? And similarly, position of center of mass stays constant if there's no net velocity. So if you're still a little confused about that, let's go over a few problems, and hopefully that will make things a little clearer for you. Okay, any questions? Alrighty, so let's do these two problems here. So I'll give you guys, how about 3 minutes to do these? because there's one last problem I really want to get to. So unfortunately, we're going to have to rush a little on these two problems. All right, so unfortunately, since we're running low on time, I think I'm going to have to cut you guys short here, and I'm going to explain these two problems now. So first, a 68-kilogram astronaut is in space, and he holds a 0.5 kilogram apple. If he chucks the apple into space at 15 meters a second, how fast will the astronaut move as a result? Well, in this case, we're going to use conservation of momentum. All right. So since the astronaut is in space, we'll assume that there is no net force, external force acting on him. So the initial momentum, if they're at rest, 0. And this must equal the final momentum. So we know the apple is moving at ma/va for mass of apple, velocity of apple. And then we're going to have, this is going to be added to the mass of the astronaut. Let's just say m times the velocity of the astronaut. Okay? So what this means is that the velocity of the astronaut will equal to mass of the apple, velocity apple, over mass of astronaut. There's a negative right there. So if we calculate all this, 0.5 times 15 over 68, v equals negative 0.11 meters a second. So what does this mean here? Well, we defined the apple's movement as positive. So this means that the velocity of the astronaut will be in the opposite direction since it's negative. So basically, the astronaut's going to move at negative 0.11 meters per second. All right. Now for the second problem, a 100-kilogram astronaut carries a launcher loaded with a 20-kilogram bowling ball. The astronaut discovers that firing the launcher results in the ball moving away from her at a relative speed of 50 meters a second. What was the impulse delivered to the astronaut when firing the launcher? Well, again, we're going to use conservation of momentum here. But the key difference between this problem and the previous problem is that this problem is very, very tricky. It says that the ball moves away from her at a relative speed of 50 meters a second. So relative to the bowling ball, the astronaut's moving at 50 meters a second. So what this means is that the bowling ball itself is not moving at 50 meters a second. The combination of the velocities of the astronaut and the bowling ball equal to 50 meters a second. So let's just say this is the center of mass. And the bowling ball is going to move this way at some kind of v1. The astronaut moves this way at some kind of v2. And the combination of these velocities, the absolute value of v1 plus the absolute value of v2 equals 50 meters a second. All right, so that's basically the trick in this problem. Now we can just use conservation of momentum here. A 20-kilogram bowling ball. Initially they're at rest, so 0 must equal to 20 times v1 plus 100 times v2. Now we have these two equations here, and then you would solve them, okay? But I'm not going to do that right now because we're running a little low on time. So do you guys understand how you do those two problems? All right. got this problem here, a little combination of energy and momentum. So if time allows, I'll give you guys 5 minutes to do this one as our last problem for today, and then I'll go over it. So once you got your answer, please chat that to me, and I'll let you know if you're right or not. Oh my gosh, who is doing that? All right, 1 more minute, and I'll explain this problem. Right, so I'm going to explain this one now. So this is a rather tricky problem, because for this one you have to combine energy with momentum. So let's read this problem. You have a spring-loaded gun in space, a 10-kilogram mass is attached to the gun, and the spring inside the gun is compressed 14 centimeters. The spring constant is 19,000 newtons per meter, and you weigh 100 kilograms. After you fire the gun, how fast will you be going relative to the mass? So at first glance, you might think, hey, well, I can use the spring constant 1/2 kx squared, and that will be equal to the velocity of the bowling ball, right? Bowling ball squared. But this is actually not right. Why isn't it right? Because when the spring compresses, it's both pushing the bowling ball forward and pushing you backwards. So not all of the energy in the spring is converted directly the energy of the bowling ball. It's converted into both the energy of you and the bowling ball. Okay, so it's not just the mass of the bowling ball, velocity of the bowling ball, it's also the mass of you, mass of person, velocity of person squared. So this is actually the energy equation we have to use, because the energy of the spring is used up in both of your speed and the bowling ball's speed. Okay, so that's the energy part of it. Now we need to use momentum, because the momentum in the system still doesn't change, right? Conservation momentum. Initial momentum is 0. So that means that means the momentum of the ball is going to equal to the momentum of you, because those two things have to balance out, right? So momentum of ball equals momentum of you, right? This is just the conservation of momentum. So now we have two unknowns, velocity of ball, velocity of you, and we have two equations. Now we can just solve for what we need. So let's first substitute VB in terms of VP. So VB equals MPVP over MB. That's from the energy equation, right? So now if we substitute MVB in here, that's going to be 1/2 MB times MP squared VP squared MB squared plus 1/2 MP VP squared equals 1/2 KX squared. Oops. Right. So now let's get rid of the 1/2. We're just going to have KX squared equals, simplify this as well, MP squared VP squared over MB plus MP VP squared. So now we'll use the distributive property, VP squared times MP squared over MB plus MP equals KX squared. So now if we move this stuff to the other side, then we'll find what the velocity of the person is. So KX squared, 1900 times 19,000 actually, 0.14, 372.4. And then what is all this? Well, mass of person squared, 100 squared, over the mass of the ball, which is 10, plus 100 equals 1100 VP squared. So now we just need to divide. Take the square root. The velocity of the person is equal to 0.58 meters per second. So now what's the speed of u relative to the mass? We need to find the speed of the mass, then we add those two velocities together. All right, so now we can go back to our momentum equation here, buried beneath all our work. Velocity of the ball equals mass of person times velocity of person over mass of ball. So then we can find velocity of ball from this equation. 100 times 0.58 over 10, 5.8. So the velocity of the ball is 5.8 meters per second. The velocity of u is 0.58. If you add those together, 0.58 plus 5.8, 6.38 meters per second. And that is the answer. All right. So there were two steps to this problem. You had to derive an equation using energy, then derive an energy using momentum, and then you would have to solve the system of equations for what you want. All right. So that was quite a difficult problem. Are there any questions? All right. So I guess that's going to be it for today. So I hope you guys enjoyed, and I'll see you guys next time. Bye. Someone's asked how many classes do we have left? I think, so next week we're going to talk about collisions and momentum. Then we're going to go over 2 weeks of rotational motion, around 2 weeks of fluids, and then around 2 weeks of statics. So we're gonna have around 7 weeks left, I'd say. All right. So see you guys later.